Okay, so this video is going to be for differential equations, section 8.2, day 3. And in this one, we're going to look at what happens when we have complex eigenvalues. Now, the last two videos, I've embedded the derivation part to show the solution form was the way it was in the lesson, but the derivation part for this is very involved. So I did include it, but I'm including it as a PDF that's posted in Schoology. So you can, if you're interested in the derivation for this kind of crazy looking form that the output is, you can see it completely derived in that PDF if you're interested in that level of detail. But we're just going to accept it as true, and I'll show you one example to show you how this works. Okay, so let's say that we've seen how to handle the cases where we have distinct real roots and also repeated eigenvalues, right, for the root eigenvalues. The third possibility is that the eigenvalues can occur in complex conjugate pairs. So we're going to need a procedure for that. The separate PDF has the understanding and everything here. We're just going to, for the derivation, I'm just going to show you the procedure. It's a little more involved. And we're going to have to do a lot more work by hand in this case, but still doable and based on what we've seen. So first, we express the system in matrix form, and we find its eigenvalues by finding the traditional determinant equals 0. Right? And when we have eigenvalues which appear as complex conjugate pairs, we write those eigenvalues in the form lambda is alpha plus or minus beta I, just like we did when we had auxiliary equations, right? All right, and then what we do is we pick the positive case. So we take lambda is alpha plus beta I, and then we use that particular lambda to solve the RREF system, where we go minus that lambda to find the system and write out the equations. Unfortunately, this means we're not going to be able to use RREF in the calculator. We're going to have to calculate we're going to have to do the calculations by hand because we can't do RREF in the calculator with the imaginary values in there. I mean, possibly we could, I guess, but typically it's not done that way. So I'm going to show how to do it by hand. Okay, that's going to result in a system of equations for relating constant 1 and 2 to constant 3 and so on. We're going to use those equations to express all the constants in terms of one of the constants, typically like K3 or K2, whichever one the last one is. And then we'll choose a convenient value for that constant to form the one eigenvector K. Okay, but that eigenvector will now have complex values, so it can have real and imaginary values in both its row and column. Okay, typically one will be purely real and the other one will be a real with an imaginary. And then we're going to find two other vectors from that eigenvector. We're going to call one of them B1, and that's going to be the vector when we take just the real parts only of the eigenvector K. And B2 is going to be just the imaginary parts of the vector K. And then the system solution is given by this. We're going to say that we're going to take X. We're going to say C1 times X1 plus C2 times X2, but X1 is we're going to take the real vector times cosine of beta t minus the imaginary vector times sine, and then all of that times e to the alpha t if there's a real part in the vector. And then for X2, it's going to be the imaginary vector times cosine plus the real part times sine, also times e to the alpha t. Again, you're just going to have to see how this looks when we do an example. So I'll do an example, actually twice. We'll do it twice to show you what this looks like. All right, so here we have a system of just two differential equations, two unknowns. It's homogeneous. And first what we would do is represent this as a matrix. So let's go ahead and do that. The matrix here is going to be X prime equals the matrix 6, -1, 5, 4, 5 times X. Okay, so there's the matrix. It's written in matrix form now. So first we need to go ahead and compute the eigenvalues. So let's do that. I'll just do this down here. So we're gonna say, all right, we have to form the determinant. So it's going to be 6 minus lambda, -1, 5, and then 4 minus lambda equals 0. Right? We attach the minus lambda to each of the main diagonal. We're going to have to compute this, so we get 6 minus lambda times 4 minus lambda and then minus -1, so plus 5, 1 times 5. So we're taking the determinant here. So we're going to end up getting, let's see, lambda, it's going to end up being lambda squared minus 10 lambda plus 29 equals 0, okay? And unfortunately, that's not going to factor. So instead, we'll have to resort to the quadratic formula. Lambda is negative b plus or minus the square root of b squared minus 4ac over 2a. And so that's going to end up being 10 plus or minus the square root of negative 16 over 2, which is the same as 10 plus or minus 4i over 2, because the square root of 16 is 4, but it's a negative square root. And so lambda ends up being 5 plus or minus 2i, okay? So we have a complex conjugate pair of eigenvalues for this system. All right, so what we'll do next is we'll take the positive version, 5 plus 2i as lambda, and we'll work with that. You know, there's actually going to be two different choices. There's going to be a choice at one point. We're going to do two ways. So I'm going to show you first one way, and you'll see when we get there. Let me use blue for this. So if I got my lambda is 5 plus 2i, we're going to go through the procedure we would normally use to produce an eigenvector for that, right? That means we would repeat the system, which is going to be 6 minus lambda, but it's going to be minus a complex value here, 5 plus 2i, and then -1, and then we have 5, and then we have 4 minus that lambda, which is a complex value, equals 0, 0, right? So that's the system we would like to put this in the matrix and do RRAF, but because of the complex numbers, we're not going to do it that way. Instead, we're going to say, okay, 6 minus 5 is 1, right? And let's see, that's going to give me 1 minus 2i here, and -1, and 5, and then 5 minus 4 is -1 plus 2i. Okay, okay, so instead of doing RRAF, we're just going to say, okay, this system right here, right now, can be expressible as two equations. So this first equation is going to be 1 minus 2i times k1 minus k2 equals 0. And the second equation is 5k1, and then plus -1 plus 2i k2 equals 0. Okay, so what we're going to do is we're going to pick one of those two equations. Doesn't matter which one. And this is where we can do it. I'm going to do it both ways so you can see that you get two different answers. Let's start by picking this equation and see what happens. So if I start with 1 minus 2i k1 minus k2 equals 0 as an equation, then I can solve one of those in terms of the other vector. So what I'm going to do is I'm going to solve for k2. It's easy to solve for that. K2 would therefore be equal to 1 minus 2i k1. And that means that my solution form is going to be, I can pick whatever k1 I want, and then k2 is going to be equal to 1 minus 2i times k1. So I can pick any value I want. So let's go ahead and pick for k1, maybe we'll pick the value 1, okay? And then that would make this 1 minus 2i. And so that means that we've got the vector is 1 minus 2i. So what happens with complex conjugates is that the eigenvector ends up having, the original eigenvector k has real and imaginary components like this. Okay, so this is the part that's not intuitive, but if you want to see the derivation for it, you can look in there. We're going to define two new vectors from this vector. The first one's going to be called b1, and it's going to consist of the real part of this vector k, the real part of k. So I'm going to make a vector, and for the first row, the real part is 1, and for the second row, it's 1. And then I'm going to take a second vector called b2, which is the imaginary parts only of k. And so that's going to be 0 for the first one, because there is no imaginary component, and -2 on the bottom. So we have these vectors for the real and imaginary parts of the eigenvector. Okay, and then we're going to use it now, basically a memorized structure that the solution, let me actually write it like this. The solution x is going to be C1 times the B1 vector cosine of beta t minus the B2 vector sine beta t times e to the alpha t plus C2 times B2 cosine beta t plus B1 sine beta t times also e to the alpha t. So this is a memorized structure that for the first term, you take the real part times cosine minus the imaginary part times sine, all times e to the alpha. And for the second one, you take the imaginary part times cosine plus the real part times time. So now I'm going to plug in all the different things. Remember, this is my alpha and this is my beta here. So that means that the solution here is C1, and then B1 is the vector 1, 1, times the cosine of beta, which is 2t, minus B2, which is 0, negative 2, times the sine of 2t. All of that times e to the 5t, because to the alpha t there was an alpha. And then I'm going to have plus C2 times the imaginary one, which is 0, negative 2, times the cosine of 2t, plus the real one, 1, 1, times the sine of 2t, also times e to the 5t. And that's it. That's how then we're done. That's it. So although it's crazy looking and it's difficult to show, and it takes, I think, 5 pages in that PDF to prove that this form works, this is the procedure for dealing with complex numbers. Okay? There's one other way that typically this is written, so you'll probably see this if you're looking in the answer key, because, and this will be nice when we do our things later, is sometimes we'll kind of write out, combine these terms together. So you might see something like this, C1, and then we'll have a vector that says 1 times, well, let me down here, it's going to be 1 times cosine 2t, and then, let's see, cosine 2t, minus negative 2, so plus 2 times sine 2t. And in the first row, it's 1 times cosine 2t plus 0 times sine, or minus 0 times sine. So you'll probably see it written this way, where we're just combining these terms together. Same thing over here. We can combine these by saying this is C2, and then we've got on the bottom negative 2 cosine 2t plus 1 times sine 2t, and on the top it's just 1 times sine 2t. So make sure that you can see how that's how that relates. Okay, so that would be the answer. Now, maybe it's bothering some of you that we didn't do anything with the second equation, right? All of that is based on just using this equation right here. Okay, in the packet that describes the derivation, I show why the book was able to derive that if you pick your eigenvector using the first equation, that same value will make the second equation always true as well. That turns out to be provable, and it's part of the derivation. But what it also means is that we could have arbitrarily decided to use this equation instead. We could have used this equation when we started. And if we did, we'd get a completely different looking answer that's also correct. So I'm going to show you those steps for that as well. Let me go ahead and clone this page, and then we'll take a look at that. So I'll just repeat this calculation down here, except I'll use the second one instead of the first, right? Because the truth is you can pick either one and they're both equally correct, right? Our goal is to find a solution to the system, not to necessarily list all possible things exhaustively. So if we were to use the second equation, I'll use red for this, then we would have 5k1 plus negative 1 plus 2ik2 equals 0. We could do that. And if we did, we could solve that now and get that, maybe solve this for k. We could say, okay, 5k1 therefore equals, if I move this to the other side, it's going to be the equivalent of 1 minus 2ik2, because it will be negative, right? Is that right? Was that minus 2i? Oh, I'm sorry, that was minus 2i. So I made a mistake there. This is minus here. This is minus. This is still minus. Let me get that right. fact, let me fix it up here. Right, this is 1 minus 5 plus 2. So that is in fact a minus there, not a plus. Minus 1 minus 2, right? This is 4 minus. There we go. Okay. So now we've got 5k1 plus negative 1 minus 2i k2 equals 0, which means if I move that to the other side, these become positive. So 1 plus 2i k2 equals 0. And then that means k1 is 1/5 of 1 plus 2i k2 equals 0. Okay, which means that the form could be, we can allow k2 to be whatever we want, but k1 has to be 1/5 times 1 plus 2i times whatever we decided k2 to be. So to make it convenient, I could choose 5 here, which makes this become just 1 plus 2i over here. So my eigenvector would be 1 plus 2i now for the x component and 5 for the y component, right? And then we would proceed the same way. We would find our b1 vector as the real part of that, which would be 1, 5. And our b2 is the imaginary part, which is 2 and 0 on the bottom. And then we would form the solution again when we write it out. It's going to end up being c1 times b1 cosine beta t minus b2 sine beta t e to the alpha t plus c2 times b2 cosine beta t plus b1 sine beta t. The way I keep that straight is there's something unusual, right? If we use these in the right order, 1, 2, then we have the minus sign. And when we have the plus sign, we have them reversed. All right, so this would therefore be C1, and then we would use the 1, 5 vector times cosine of 2t, beta is 2, minus the 2, 0 vector times sine of 2t, e to the 5t. And then we've got plus C2 times the b vector, 2, 0, cosine 2t plus the b1 vector, the real vector, sine 2t times e to the 5t. Or more commonly, it would be written this way probably, with cosine 2t minus 2 sine 2t for the top row and 5 cosine 2t for the bottom row times e to the 5t. And then plus c2 times, and we've got 2 cosine 2t plus sine 2t, and then down here we have 5 sine 2t e to the 5t. So this is the general solution for the entire thing, for the homogeneous system. Right? And you'll notice that that looks quite different than what we got on when we chose the first equation, right? We have 2 equations on the bottom here and 1 equation on the top, whereas this one has 2 equations on the top and 1 on the bottom. But both of those are considered fully correct. You don't have to do both of them. You just pick one of the equations, and that's correct. All right. So just one big example to explain it here, and hopefully that's enough for you to go ahead and try. Remember, though, when you try that you might not get something that matches. So if you're consistently not able to get them to match, maybe try the other equation to see if you can get that to match. Right? There's many possible forms here. Also, these constants could be different too, but they would be multiples. Because like at this stage, I could have picked, I could have picked up here a 5, but I could have made this a 10, right? I mean, I could have made this a 10, but then everything here would be double. Right? So, what you get should either match the solution or it should be something where the constants are multiples of the solution in the book. But if you can't make that match that way, then try the other equation if you're trying to check to see that it matches. Okay, if you're checking work. All right, and that's it for this video.